In this lecture, we're going to look at the idea of unit testing and test-driven design. In very simple terms, unit testing is the idea of breaking down a programming problem into tasks that are small enough and simple enough that they can be tested very easily. Test-driven design is the idea of starting to write your tests before you write any code. Unit testing then is a very important concept in all languages. However, like version control, which we'll do in another session, is often missing from introductory programming courses. Here, of course, we focus on Python, but the concepts that I'm trying to introduce are very general. Unit testing can be defined as a method of testing individual units of source code to determine whether they are fit for use. This, by its nature, requires really modular design of your code, breaking your problem down into separate functions or methods that are simple to test. The smaller the subroutine or the method, the easier it is to test. And the more testing you perform, the fewer bugs you're likely to have in your code. So why should we do it? Well, individual subroutines are much easier to test than whole programs. Testing a whole program really is a very difficult thing to do when you're doing something complicated and involved like the project work that you're doing. Whereas if you can split it into simple enough tasks that we can test, then the chances of the whole program working are much greater. Secondly, unit tests can be standardized and automated. This means that as you make changes to your code, for example, supporting some new feature, you can run the unit tests and make sure that the old part of the code still works properly. Automated testing then allows extensive testing to be made after such changes are made to the code. Introducing just a small new feature can so easily break a much larger, more complicated system, and this really gets around that problem. Finally, tests also act as a way of documenting your code, because your test should show all the likely different ways of calling a particular method or function. In this diagram, I illustrate the anatomy of a test. Essentially, what you have to do is do some manual calculation. Some expected results are going to have to be generated, which is how you expect the function that you're writing to perform. So on the right hand side of the diagram, we're showing some sort of manual calculation, maybe looking up numbers in a reference book or something like that, that give you an expected result. And on the left hand side, we're implementing the subroutine and producing an actual result. And then at the bottom, we're testing whether the actual result matches the expected result. Let's take a look at a simple example then. Here what I've done is implement a simple function called sine square. Now I've documented it using a doc string, and as it says, what this does is to return the square of a number, but if the number was negative, the return value is also negative. So if we find the square of +1, that would be 1. The square of -1 would also be +1, but with this routine it would return a value of -1. So in the code I've implemented a simple way of doing it. It's not particularly neat, but it's functional. I'm passing a value in here. If this value is less than 0, I set the sign to -1. Otherwise I set the sign to +1. And skip over the comments here, and I've got square equals value times value, and then I return the sign times the square. So that looks like it should function properly, and let's add a piece of test code to check whether this works. The way that we can do this relies on the fact that you're going to be using modules to implement your code. The test code then makes use of a special variable called underscore underscore name underscore underscore. Now this special variable stores the name of the module that we're currently in, and if we're running the main piece of code rather than running an external module, that will be set to underscore underscore main underscore underscore. So by putting a piece of code into your module that contains this if statement, then if we try and run the module as a program instead of importing it as a module, then this piece of code that follows will get run. If we try and use it as a module, then this will simply be ignored. What I've done within this section of code then is to provide some simple tests. I've taken a sine square of 2, a sine square of 0, and a sine square of -2. So we know from our definition of what the sine square routine should do that in this first case we should get +4, second case obviously we should get 0, and in the third case we should get -4. So I've just followed this by a simple bit of code saying if the value is not equal to 4, print the method failed, otherwise print it succeeded, and so on through the different tests. So you can download this by clicking the download link. I've got it downloaded already, so let's go and have a look at this. I'll just show you the piece of code just to prove that it's the same with the tests here. And if we run this, you can see that the routines all succeed. Now let's just introduce an error. So I'm simply going to put in a mistake here, just leave this as 1 as well. And if we run this, you see that now the sine square on the negative number, as you'd expect, has failed. Okay, so that's all very well, it works as it should, but it's not terribly neat. If we scroll down, then here's a slightly better version of the code. In this case, the actual code for sine square is exactly the same as it was before. But now I've implemented a new function called run test one return. So this is a simple subroutine that takes a name as input, which is the name of the subroutine being tested, the input that we're giving to the subroutine, the expected output, and the actual output. And all we do is say if expected equals actual, then we print success. We give the name of the function and the input that was given to it, and if the function failed, in other words the expected and actual values were not the same, then we print fail, and we give the 4 values here. So the way the function was called, the name of the function and its input, and we say its expected output was this, but the obtained output was this. So in our test, we've tidied up this a little bit as well. As you see at the bottom, the main program that runs when we run this as a piece of code instead of as a module calls a routine called test sine square. And we've defined test sine square to run tests on values of 2, 0 and -2 with the expected results of 4, 0 and -4. And here we're calling the sine square method with those values to return the actual values that we observe. So again, you can download that by clicking on the link here. I've got it downloaded already. So if I run that, you can see that the code succeeds. Everything says success. And again, if I edit that piece of code and introduce an error, so the actual sine square we'll put in here, turn 0, and we run the code again. You can see this time, because the error that I put in, the sine square of 2, we were expecting a value of 4, but we obtained a value of 0. This way of doing testing, to be honest, I use this sort of thing quite a lot. It's quite simple, quite straightforward, avoids you having to use any other external packages to do your testing. It's, as I say, simple and straightforward, and for a lot of things it's perfectly functional. There's no reason not to do it this way. Test-driven design or test-driven development is the idea of writing the tests before you start to write the code. This really then keeps you focused on the program's requirements. It ensures that the code you write is written to be testable. So by thinking of your tests before you think of writing the code, you know that your code has got to be testable. It encourages you to write manageable modular code, and it encourages the design of fixed application programming interfaces, which again is so important for your project work. Let's look at the anatomy of test-driven development, how we actually set about doing this. We start off by writing a test, and then we check whether the test succeeds or not. Obviously it won't at this stage because we haven't actually written any real code. So the test will fail and we can write some production code. Now we run the tests that we have again and see whether the tests succeed or fail. If any of the tests fail, we go back and write more production code, and we sit in this loop until finally all the tests succeed. We then might go through a process of cleaning up the code, just tidying things up, adding all our comments, maybe making sure that all our variable names are appropriate and altering those, adding our doc strings, all that sort of thing. And then we go back to the very beginning. We maybe write some more tests, and we check whether those tests succeed. If any of them fail, we go through, write more code and keep working through this until hopefully we get to this stage and our tests succeed, and we just write maybe some more tests. Once you think you've written all the necessary tests, then you can stop the process. If you follow this link to Wikipedia, you'll get some more information about the idea. In test-driven design, designing your application programming interface, your API, is absolutely crucial because you're going to do that before you start writing any code. So you need to decide what the subroutine, the function or the method will be called, what arguments it will take, how those arguments are going to be encoded. So we might decide to use an array, we might decide to use a dictionary, and so on. There are different ways of encoding the same information. We need to decide what our routine is going to output and return, and we need to think of some test cases. So how do we think of test cases? What do we need to test? Well, we need to test normal or expected data. We need to test what's known as edge cases, and I'll come back to those in just a moment. We need to test data that should fail and make sure that it does give a failure, and data that should give errors and will fail cleanly. So there's a bit of a difference there between an error and a failure. An error is where the code is getting data that it does not expect, and a failure is the response that the code makes to getting those data that it doesn't expect. So in terms of failing cleanly, we need to return something to the calling code to say that there was a problem. Let's look at this idea of edge cases and look at an example based on a simple piece of geometry of overlapping rectangles. So the correct behaviour for edge cases depends largely on the application for which we're writing the code. In this particular example, we have two potential edge cases which are shown at the bottom. So one edge case is where one of these rectangles just touches another rectangle side to side, and another edge case is where the two rectangles touch corner to corner. Above this I show the standard input examples. So the first one, the two rectangles clearly do not overlap. In the next one on the right we have one corner overlapping. In the middle row then we have two corners overlapping. In the middle example we have no corners overlapping, but clearly the rectangles themselves overlap. And in the third example there we have one rectangle fully inside the other one. In the case of the edge cases here, whether we want to define these as overlapping or not, as I said, depends on the application that we're writing this code for. If the application was something like fields, we think of fields in a farmer's field, something like that, then clearly the edge-to-edge case, one could move from one field to another without having to leave the farmer's land. In the corner case, again, depending on the resolution of our measurements, we may be able to move from one to the other without leaving the farmer's fields. Perhaps the resolution is only to 1 metre, and therefore we've actually got a fair amount of space to be able to move from one to another. In this sort of approach, debugging fits within our test cycle and our test-driven design cycle. Of course, we hope by defining a sufficient set of test cases, as we've done here, so we've got 1, 2, 3, 4, 5 normal test cases and 2 edge cases. By defining a sufficient set which covers all the likely scenarios that we're going to have, we would hope that we're not going to have any bugs anyway, because we'll have tested these things. But of course, bugs always creep into code. So in the case of debugging, we know that the program fails, but we would hope that all the unit tests have passed. In this case, what we need to do is add new test cases that test this particular problem set of data. And we would run the test, and if the test passes, then we know that this test case is not appropriate. We need to find a test case where the test actually fails. Once we do that and the test fails, then we can go on to try to fix the code, run the test, and the test should fail again. We keep repeating this until we really have fixed the code properly. And then we can go back and test all the unit tests again and make sure that in fixing this bug we didn't break something else. One of the things that we can do then with testing is to automate the process of testing. If we continue to the next slide, we find that many languages provide frameworks for automating this testing. And when we have examples like this where we add a new feature or we fix a bug, then automating the testing to make sure that everything that was there before still works properly is really a very good way forward. So as I said, many languages provide frameworks for automating this testing process. In Python, there are systems called unit test and py.test, and another one which is much simpler, which is what we're going to focus on here, called doctest. If you're doing more advanced testing, then unit test and py.test are the way to go. But for the process of this demonstration, this lecture, we're just going to look at doctest. In Perl, there's a system called test more. In C, there are various alternatives: check, ace unit, GNU auto unit, C unit, capital C unit, min unit, and so on. C++, there are ones like cpp unit, cput, cpp test, and in Java there's one called junit. And you can follow this link to Wikipedia to find a list of unit testing frameworks. As I said, here we're going to focus on doctest because it is very easy and simple to implement. It's what the Python experts refer to as Pythonic. It's very simple. It makes use of the Python style of doing things. And a big advantage is that it's part of Python's standard library, so you don't need to add any extra libraries or modules in order to make use of it. Let's take a look at a simple example. This is a piece of code that creates a Fibonacci series. It includes some simple test code, and as we saw previously, the test code is only executed if this is run as a program rather than being imported as a module. First of all, we'll do some simple manual calculations to work out some examples. So the Fibonacci series for 0 is defined as being 0. What we do in a Fibonacci series is to take two numbers, which we start with 1 and 1, and we add them together to give 2. Then we add the last two numbers, and that gives us 3. Add the last two numbers, that gives us 5, and so on. Doing this, the Fibonacci series then for 10, so we're doing 10 steps, the value should be 55, and similarly the Fibonacci series for 15 should be 610. Here's a piece of code that implements this then. To calculate the nth Fibonacci number, we're just using quite a Python-esque way of doing this. We're setting the list AB to the list 0 and 1. This is our starting point. And then for I in range up to n, so we're going up to the value 10, for example, then the list AB is set to B and A plus B, and we return A at the end of doing this. Here's our way of calling our test code. So we say if underscore underscore name underscore underscore equals underscore underscore main underscore underscore, then we run the test code. And I've put in 3 simple examples here. If the Fibonacci of 0 equals 0, and of 10 equals 55, and of 15 equals 610, things we calculated above, then we print that the test was okay, otherwise we print that it failed. Again, you can download this piece of code here, but we'll have a look at it over here. So I'll show you this piece of code first of all. Here it is, and I can run it, and the test succeeds. So let's just edit it so that it fails. Let's just put in +1 or something like that and run it again. And there we see it says the test failed. Let's put it back so it works again and run it once more so it's okay. This is the sort of test we used before. It's all very well, but it would be nice if we could do something a little bit more clever. And the way that we're going to implement that is to use doctest. Now the nice thing about doctest is that it allows us to include the test within a documentation string. And the way that we format the test is as if we were running Python interactively and getting the results from that. So we'll do exactly that. Let's start up Python 3. And we will import the fib function from the fib1 module. So now we can try some test cases. We can try the value 0. We can try the value 10. And we can try the value 15. So what we do is to take this piece of code and cut and paste it into your code. So this is shown in the example below. And you can see here it just goes into the doc string. So let's add this into here. So I'm just going to make our doc string span a few more lines, and I'm going to cut and paste my code into there. So as you can see in the example here, or in the example here that I've just put in, we're putting the code exactly into the doc string. We're indenting it so that it looks neat with everything else. Now, what we need to do, as we see here, is instead of having our test in here, we'll just remove this. We'll just import doctest, and then this function here, doctest.testmod, runs the tests. So again, if I now just quit from this and I now run my modified version of fib1, you can see it completes and nothing happens. Get nothing back. So that is the indicator of a successful test. Now if I make a mistake in my code and run again, now it tells me that it failed on fib10. So we were expecting 55, but we got 143. It failed on fib15, we expected 610, we got 1596. So it tells us at the end that we had 2 failures in the code. This is just demonstrated below here. Everything okay, we get nothing back. When there's an error, we get a message telling us what we expected, what we should have seen and what we did see. Moving on then, we'll take our example that we looked at previously of overlapping rectangles and how we can use this with proper test-driven design. So once again, The project specification, or the specification for this specific piece of code, is that given the coordinates of two rectangles, we want to create a program that can determine whether these two rectangles overlap. As we mentioned earlier, before we start writing any code, we design the tests and we design the API for the function that we're going to write. So we need a specification for our code. First of all, we need to decide what will the subroutine be called. We need to make sure that our subroutine name is descriptive. So in this case, something like "do rectangles overlap" is a good descriptive name. Then we need to decide what arguments the subroutine is going to take. Now, in this case, we have a number of choices. Specifically, we could choose the XY coordinates of all four corners. But if we make the assumption, or it's not necessarily an assumption, it's part of the project specification, that the rectangle will always have lines, sides that are parallel to an x-axis and a y-axis, then we only need the bottom left and top right hand corners, or of course top left and bottom right hand corners. So in this case, that's all we actually need to pass in. We then have to choose how we're going to pass these pieces of information into the subroutine. We could do it as 8 scalars, so ax1, ay1, that would be the bottom left of rectangle A, ax2, ay2, top right of rectangle A, bx1, by1, that's the bottom left of rectangle 2, and bx2, by2, the top right of rectangle 2. That would be one way of doing it. Another way would be as a list, the same pieces of information but in a list rather than in separate scalar values. Or it could be two lists, the x1, y1, x2, y2 of each of the two rectangles. Or it could be a dictionary where the keys are the names of the coordinates. Or it could be two separate dictionaries where the keys are the names of the coordinates, so x1, y1, x2, y2 for one rectangle, and then another dictionary for the second rectangle. So in this case, that's what I've decided to do. I've decided to use two dictionaries, each of the form A equals and then x1, y1, x2, y2 as being the keys and a set of values. This is the sort of thing, again, that you're going to need to decide in your coursework exactly how you're going to pass bits of information backwards and forwards. And then we need to decide what the subroutine will return. In this case, we need to know whether the two rectangles overlap or they don't overlap. So the logical thing would be to return true if they overlap and false if they don't. So in Python, of course, we do that simply by returning the values true or false. Now, we've already looked at this diagram. This is our test data and example test cases. Of course, in reality, there are an infinite number of possible test cases, and you have to decide on an appropriate level of detail to test. You must be sufficiently thorough and attempt to identify all categories of possible data. And then you need to decide how many examples you're going to give in each category. And probably in most cases, simply giving one example for each category will be enough. So that's what we're going to do here, design one test for each of the categories given in this image. We also, as before, need to define the behaviour of those edge cases. So whether two rectangles touching count as an overlap is going to depend on the specification and what we're using this tool for. Going through this process of looking at test cases, identifying edge cases, will help you to determine the correct decision to be made about those edge cases before you start writing any code. We're going to start off by making the decision that the rectangles where the edges touch or the corners touch do not overlap. The next thing we're going to do then, having done that analysis, is to write the tests. So we're going to create a dummy routine that returns some arbitrary value. In this case, rather than returning true or false, I'm going to return bug. Before each test, we create our test data. In our case, we're going to be creating two dictionaries that model each of the rectangles. We're going to experiment with the command line to check the formatting, as we did in the Fibonacci example. And we're going to decide on the expected result for each test. And remember, this is largely going to be a case of, for these examples, this one will return false, they don't overlap. All these ones are going to return true because they do overlap. And then the bottom two edge cases are going to return false because we've determined or decided that these are not going to overlap. What we need to do then is add a comment for each test line into our doc string, and also put in a comment to describe what the test is doing. This makes it easier to understand the output. Once we've written our tests, we can run the code. And of course, we haven't written anything of the actual code other than a dummy routine returning an arbitrary value of bug. Let's have a look then at what the code looks like. Our do rectangles overlap routine then is defined, let's move down to the bottom of it here, returns bug. But we have this big long doc string where we've defined a set of tests. So we define rectangle A as being this, rectangle B as being this. This was an example where they don't overlap and they don't touch. So when we call do rectangles overlap AB, then we expect a return value of false. Then we choose one with one corner in the other rectangle, we return true. Two corners in the other, return true. Overlapping but no corners contained, so this was this example in the middle here. And again, we want that to be true. One rectangle containing the other, true. And one edge touching, we've defined that as returning false, and one corner touching, return false. Let's have a look at the code then. Let's exit from this. Okay, so let's just make the window a little bit bigger, and you can see this is our code with all the tests and the actual code itself just returning bug. Then, as before, if the name is main, we'll import doctest and do the doctest.test mod. Let's run that piece of code then. And of course everything fails. It was expecting true or expecting false and instead getting a value of bug. So we're told there were 7 failures, and we know here that we had these 7 tests corresponding to the 7 examples in the diagram. Okay, again you can download that by following the link. Now we need to start implementing some code. We've got the tests, we've designed an API and a complete specification of the subroutine. We know what the tests should produce when run on a wide range of different types of example data, and this makes writing our subroutine much easier. If we look here then, we have our code exactly as it was before with all the tests, and at the bottom here's our implementation. If x1 for rectangle A is less than that for b, and x2 is greater than that for b, and y1 is less than b, y1 of a is less than y2 of b, and y2 of a is greater than y1 of b, then we return true. This is a kind of one-line implementation. Of course, there are other ways of implementing it as well, which might be a bit clearer to read, but this is kind of the most compact way of doing it. So if we have a look at this piece of code, this should be in Geometry 2, and we run it, we find now we've got no result coming back, which indicates success. So let's just introduce a bug. So let's just change that greater than sign to a less than sign. Run the code again. And now we have 4 failures out of the 7 in total. And as you'll see, because I put a comment on the function calls, or the example function calls here, in the docstring to indicate what this was testing, then you can see here it tells you specifically which tests failed. Otherwise we just see do rectangles overlap failed. So give you the line number, of course, but it's easier if you have a comment that lets you identify what the test was testing. So let's just correct that again, run it again, and now we get nothing. Okay, so that's all worked rather nicely. If we continue on, then we can have a look at how we can use this to deal with changes in specifications. If we take a look at the diagram here, at some point after completing our code and everything's working fine, the specification has changed such that now the touching rectangles are required to be defined as overlapping. So what do? The specification changes. We need to change the tests first of all to fit the new specification. We run the test. If the test passes, then we might introduce a new test. At this stage it really shouldn't pass because we've changed the specification, so there's something wrong in our test. We need to keep doing this until we find a new test that causes the test to fail. We then fix the code, run the test. If it fails, we fix the code again, and eventually, hopefully, everything will work. By having this docstring approach, we're automatically going to test everything every time. We don't just test our one example for which the specification has changed. Everything will be tested. So let's have a look at this. If we look at this piece of code, then go down to where the actual implementation is, and you can see that's unchanged from what we had before. All that we have changed is those last 2 tests where we had one edge touching and one corner touching. We've changed these such that they're expected to return true rather than it returning false. Let's have a look at the code. Let's shut this one down. Again, you can see here this is the implementation unchanged. Here we've got true and true instead of false and false that we had before. So if we run this one, and you can see that everything has passed except for those last 2 tests where one edge touching and one corner touching, where we expected to get true but instead we got false. So what we can do now is implement the changes to the code to fix the problem. And now all we need to do is change all the less than and all the less thans to less than or equal to, and all the greater thans to greater than or equal to. So let's just try that. So I'll just run this one again so you can see that those two last tests failed. Now we go down and edit the code so it's less than or equal to, greater than or equal to, less than or equal to, greater than or equal to. Save that and run the code again. And now all the tests pass once more. Okay, in conclusion then, testing a whole program is very difficult. It's really tricky to try to make sure that all of your underlying pieces of code have every possible scenario run through them. If you test those individual pieces of code separately, then you've got a much better chance of exploring all the possible scenarios. So break your code up into small testable units and put those into a Python module or more than one Python module. Define your API, think about what input data should be tested, write tests before you write the code, then you write your code, and hopefully more testing means fewer bugs, means less work and more happiness.